Hello! In this video, we are going to prove the following theorem. Suppose f and g are Riemann integrable functions on a comma b. And suppose f of x is less than or equal to g of x for all x in a comma b. Then the integral of f is less than or equal to the integral of g. Now, let's first remind ourselves of some things. So if we consider our closed interval a comma b, let's say it looks something like this. Well then, a partition of a comma b is a collection of non-overlapping closed intervals whose union is a comma b. So for example, this collection of closed intervals would be a partition of a comma b. And we might label these intervals I1, I2, and so on. We might label the endpoints of the closed intervals x0, x1, x2, and so on. So in general, a subinterval II would be given by xi minus 1, comma xi. Now a tagged partition is when we select a point from each subinterval. And let's say that the points that we select are these. The points that we select are what we call tags, and we might label the tags T1, T2, and so on. So this would be a tagged partition of a comma b. And we can symbolize a tagged partition by a letter with a dot on top. And in the collection, we have a collection of ordered pairs. The first coordinate of an ordered pair is the subinterval. The second coordinate is the tag belonging to the subinterval. So this would be the tag partition given above. Now, the norm of a partition is the length of the longest subinterval of the partition. So in that case, the norm of this partition would be the length of the subinterval I2. And the way that we symbolize the norm of a partition is with double vertical bars, like this. So now, let's talk about the definition of a Riemann sum. Given that f is a function from a comma b to r, and p is a tagged partition of a comma b, we'll say that the subintervals of the partition look like this, and the tags of the partition look like this. Then the Riemann sum of f corresponding to p is given by this formula. And really what's going on here is we're adding the areas of a bunch of rectangles, where the width of each rectangle is the length of each subinterval, while the height of each rectangle is the output value of f at each of the tags. Right, so that's a way that you can think about this visually. So now let's talk about the definition of a Riemann integral. By definition, to say that f is Riemann integrable on a comma b means the following. It means that there exists a real number L such that for every epsilon greater than 0, there exists a delta greater than 0, such that for all tagged partitions of a comma b whose norm is less than delta, we have that the absolute value of the Riemann sum minus L is less than epsilon. Now, we have proven that this real number L, which satisfies this statement, is unique. And we denote L as the integral from a to b of f. So I'm just going to go ahead and replace L with this notation. Similarly, to say that g is Riemann integrable on a comma b means the same thing as this. It's just, instead of dealing with the function f, we're dealing with the function g instead. Okay, so now let's get into proving this theorem. Now the whole goal is to prove that the integral of f is less than or equal to the integral of g. And to prove that, we'll assume for contradiction we instead have the integral of f is strictly greater than the integral of g. Now, since f is Riemann integrable on a comma b, this means that this statement is true. And this statement works for every positive real number. So in particular, it must work for the positive real number integral of f minus integral of g over 2. So taking epsilon to be integral of f minus integral of g over 2, well then, there exists a positive real number I'll call delta 1, such that for all tagged partitions of a comma b whose norm is less than delta 1, we have that the absolute value of the Riemann sum minus the integral of f is less than the integral of f minus the integral of g over 2. And since g is Riemann integrable on a comma b as well, we can do the same thing for g. So taking epsilon to be integral of f minus integral of g over 2, well then there exists a positive real number I'll call delta 2, such that for all tagged partitions of a comma b whose norm is less than delta 2, we have that the absolute value of the Riemann sum minus the integral of g is less than integral of f minus integral of g over 2. Now certainly, there exists a partition of a comma b whose norm is less than both delta 1 and delta 2. In fact, for any positive real number delta, there exists a partition of a comma b whose norm is less than delta. The reason why is because if we consider an arbitrary positive real number delta, well then, by the Archimedean property, there must exist a positive integer n, such that n is greater than b minus a over delta, right? Given any real number, we can always find a positive integer bigger than it. So then, multiplying delta to the other side and dividing n to the other side, this gives us b minus a over n is less than delta. So all we have to do is consider the partition of a comma b with n equal subdivisions. Well then in that case, the length of each subinterval will be less than delta, and therefore the norm of that partition is less than delta. So yeah, this shows, given any positive real number delta, we can always find a partition of a comma b whose norm is less than delta. So in particular, if this positive real number is less than both delta 1 and delta 2, then we can find a partition of a comma b whose norm is less than both delta 1 and delta 2. And let's call that partition Q. We'll say that the subintervals of Q look like this, and the tags of Q look like this. But now, since the norm of Q is less than both delta 1 and delta 2, well, we can use the previous two statements that we just asserted, introducing delta 1 and delta 2. Since the norm of Q is less than delta 1, while replacing P with Q, we have that this statement is true. And also, since the norm of Q is less than delta 2, then over here, replacing P with Q, we have that this statement is true. But then, notice these two inequalities are both of the form absolute value of A is less than C. And a property of absolute values tells us that this is equivalent to saying that A lies between negative C and positive C. So this means for this inequality, we can say that the quantity inside the absolute value lies between the negative of this value and the positive of this value, and similarly for this one. Now notice, if we focus on the right-hand side of this inequality, and we add integral of g to the other side, well then we can combine it with this fraction, and we're going to get integral of f plus integral of g over 2. We can also obtain the average of integral of f and integral of g by manipulating the left-hand side of this inequality. So notice, if we move the negative sign into the numerator, well then, this is actually the same thing as the integral of g minus the integral of f over 2. So then, adding integral of f to the other side and combining it with this fraction, well that's going to give us integral of g plus integral of f over 2. Or in other words, integral of f plus integral of g over 2. So, putting these two inequalities together, this shows that the Riemann sum of g is less than the Riemann sum of f. And so now, let's condense this information into our proof. So, with this assumption that the integral of f is greater than the integral of g, we have been able to deduce that the Riemann sum of g is less than the Riemann sum of f for this particular partition. But let's use the fact that we haven't used yet, which is that every output value of the function f is less than or equal to the corresponding output value of the function g. The claim is, with this fact, we can show that the Riemann sum of f is less than or equal to the Riemann sum of g, which will contradict the fact that Riemann sum of g is less than Riemann sum of f. And to see how that happens, we'll notice by definition of a Riemann sum, the Riemann sum of f with this partition is this. But now, let's think about the terms of this sum. Since every output value of the function f is less than or equal to the corresponding output value of the function g, well then, in particular, this is going to be true at each of the tags. So, we have f of t1 less than or equal to g of t1, f of t2 less than or equal to g of t2, and so on, all the way up to f of tn is less than or equal to g of tn. And now what we're going to do is, we're going to multiply the length of each corresponding subinterval on both sides of these inequalities. So we'll multiply x1 minus x0 on both sides, x2 minus x1 on both sides, and so on. And so what this shows is that each term of this sum is less than or equal to these corresponding values. And therefore, the sum of all these guys must be less than or equal to the sum of all these guys. And by definition, this is precisely the Riemann sum of g. So this shows that the Riemann sum of f is less than or equal to the Riemann sum of g, which contradicts the fact that Riemann sum of g is less than the Riemann sum of f. Our assumption that the integral of f is greater than the integral of g led us to a contradiction. So we must instead have that the integral of f is less than or equal to the integral of g. And so this completes the proof. And so yeah, that's pretty much it for this video.